In the previous videos, we have obtained the action of a point particle moving in a gravitational field, and we have also derived equations of motion that express that the proper acceleration of the particle is zero if it is a free-falling particle. If you add other couplings to other fields, then there is a force that appears in the right-hand side of the equation, and then the proper acceleration times the mass is equal to some force. In this video, we are going to study some general properties of the equations of motion related to conserved quantities, and that facilitate the integration of those equations. Remember that when we studied in general the Lagrangian equations of motion, the Euler-Lagrange equations, we said that if there is a cyclic coordinate, a coordinate that does not appear explicitly in the Lagrangian and the action, then there was an associated constant of motion or conserved quantity. Later on, we took a more general perspective, and we said that okay, the association between conserved quantities or constants of motion is not just with cyclic coordinates, but with symmetries of the action. And there is a relation between cyclic coordinates and symmetries, because if there is a cyclic coordinate, we argue that simply the action will be invariant under constant shifts of that cyclic coordinate. The question is that the cyclicity of a coordinate clearly depends on the coordinates that we are choosing. So you can see that a coordinate is cyclic if you choose certain coordinates, but now you change coordinates, that coordinate disappears, and you may not see clearly that there is any missing any cyclic coordinate anymore. If there is a symmetry, clearly there is a symmetry after and before. It's just that this shift symmetry takes a much more complicated form. Now we would like to find a more precise relation between these cyclic coordinates and symmetries, and we are going to do it to try to explore this problem in without fixing any coordinates and assuming anything. So all we are going to say from the beginning is that okay, we have the action for a point particle, okay, and let me forget about proportionality constants, okay, because now what we care about is the invariance, and the proportionality constants do not do anything about it. We have this action in a general background, and we are going to consider transformations, infinitesimal transformations of the coordinates of this form. Instead of writing epsilon mu as we have done often, let me separate an infinitesimal parameter and a vector field k mu. Okay, so these are the transformations that we are going to study. If there is a cyclic coordinate, then we know that this, for a particular k that only has a component in the direction of that coordinate, this action will be invariant. Now we want to study the general case without assuming anything about cyclic coordinates or anything. So let's see how the action transforms under this symmetry. Well, under this transformation, because we don't know yet when it is at symmetry. It only acts on the x's, so psi is still there. We have 1 over 2, the square root of all that, and then we have the variation of g mu nu, x dot mu plus g mu nu, and as usual 2 times the variation of x dot mu. Well, the next step will be to take the partial derivatives of metric. This is what we have done also many times. And here we can commute the derivative and the variation. We know that this gives 2 times the derivative with respect to psi of delta x mu, and then we have g mu nu x dot nu. And as usual, we are going to but in this case, we are not going to integrate by parts or anything. This is what we usually do to find the equations of motion. But here in this case, okay, I am going to replace this transformation by this form of the transformation. So let me write this as epsilon. Epsilon will appear here as a common factor. Okay, so I already put it here. Have k rho, and here we have k mu. And now we have to take the derivative of k mu with respect to psi, and for this we apply the chain rule. And this will be partial rho k mu, and then x dot rho g mu nu x dot nu. Let me choose indices so that I can take a common factor x dot mu x dot nu. So I will call this rho and this mu, which means that this is mu, and here I have rho and nu. And okay, I have x dot nu, which is a common factor of partial rho g. So order in this way is better, plus 2 times partial mu k rho g rho nu. Okay, the question is, when is this asymmetry? When this delta epsilon of s is equal to 0. Okay, there are no total derivatives, so the only possibility is that this factor vanishes identically. So this is 0 if this is 0. This equation, which we have met before but written in terms of some epsilon instead of epsilon mu instead of k mu, okay, can be written in another way. I think I explained this, that first you replace these partial derivatives by covariant derivatives, realizing that all the terms that contain the connection cancel. So the first step is just that, and you can check the video in which we did this. This is completely valid. Then this is 0 because it is the covariant derivative with the Levi-Civita connection of the metric, and we can lower the index of rho, and we also have to take into account that okay, this is only the symmetric part in mu nu of this equation that counts, because this is symmetric in mu nu. So really the equation that we have is this, and when I lower the index rho, what I get is 2 times mu k mu equal to 0. And remember that we even gave a name to this equation, which is the Killing equation. Well, now I'm not sure that I gave this name, but if I didn't give it, I give it now. This is the Killing equation, and any solution, any of this equation, so any vector that satisfies this equation is called a Killing vector. and it's killing with capital K because it's the name of somebody. Okay, and okay, so this is the condition when the K is a vector that satisfies this equation. So it is a killing vector. Then this transformation lives invariant the metric. Okay, this equation is an equation that clearly depends implicitly of the metric. So it's a killing vector of the metric G mu nu. A certain metric may admit more or less killing vectors. For each of these killing vectors, there is an associated symmetry, okay, which are shifts, well, not in just one coordinate, but in the direction in which this vector points. Okay, that leaves invariant the corresponding action for a point particle moving in that background. The last thing I have to say about this is that the transformation of the metric under a general coordinate transformation of this form, okay, is precisely this. Okay, up to, well, now I am calling this epsilon. So you want to, well, I can put epsilon as a common factor, and here this is K. So clearly, when K is a killing vector, the metric is invariant under coordinate transformation, general coordinate transformation of this form. We say that this coordinate transformation is generated by this vector field. So we can say that this is 0 for general coordinate transformations generated by killing vectors. They may exist or they may not exist. If they exist, this is a property of G mu nu, and the property is that it is invariant under this general coordinate transformations. When there is a general coordinate transformation or a diffeomorphism that leaves the metric invariant, okay, this is the invariance of the metric, we say that there is an isometry. So killing vectors generate isometries. And this is what you have to keep in mind. There is a one-to-one association between isometries and killing vectors, transformations that live invariant the metric. But there are some trivial examples where the metric clearly is independent of one coordinate. We know that the metric is invariant under shifts by that coordinate. Okay. I have a metric like this. So if it doesn't depend on a certain coordinate, whatever x it is, well, if I say x going to x plus some constant, these differentials are invariant, and the metric is invariant if it does not depend on x. So this reproduces basically what we said before, but there will be a killing vector associated to this. I'm going to explain this relation between cyclic coordinates and killing vectors more precisely now. And the explanation is based on a theorem that tells you the following. If you have a killing vector, killing for the metric G mu nu, then there exists some coordinate system. I'm not going to change the name of the coordinates, but there will be some new coordinates such that in those coordinates, which are called adapted coordinates, so these are coordinates adapted to this killing vector or to this isometry, such that for one of them, okay, well, two things happen. First of all, K mu is just given by delta mu and the coordinate and certain coordinate. This is usually called the adapted coordinate, but sometimes you may have to do more in this coordinate transformation. You may have to change more coordinates. So this is why we talk about adapted coordinates in plural, but this is the adapted coordinate. This means that k mu, partial mu, is just a partial derivative with respect to this coordinate. And this is the first fact, and the second fact is that the metric is independent of that coordinate. So this is a bit the converse of what we were saying. When there is a cyclic coordinate, it is obvious that there is a killing vector. Precisely of this form, if C is cyclic, then automatically you can check that there is a killing vector. We can do it now, because the killing equation that we wrote in this with the covariant derivatives, but we have another expression for it. Okay, so k rho partial rho g mu nu minus partial mu k rho g rho nu minus partial mu k rho g mu rho equal to 0. Now, what I'm saying is if there is a cyclic coordinate, if C is a cyclic coordinate, then there is a killing vector which is precisely of this form, and we can prove it, because if g mu nu is well, if C is a cyclic coordinate, g mu nu is independent of C, but k, the k that we have chosen, is precisely such that this is the derivative with respect to that coordinate. So this first term will be just this, and by definition of cyclic, it vanishes. And these two terms vanish because the components of k are constant. So indeed this k that we have written here is a killing vector when C is a cyclic coordinate. And now this proves the converse. Now you have a generic killing, which can be very complicated, and depending on the coordinates, a very complicated way. There is always a change of coordinates such that you can bring the vector to this simple form, and such that the coordinate associated, the adapted coordinate, is cyclic, in the sense that the metric is independent of that coordinate. And cyclicity is a property of the Lagrangian. I always referring to this Lagrangian. So when the metric is independent of that coordinate, this Lagrangian, this action, are invariant. Okay, there is a question that you can ask now, which is what happens if I have more than one killing vector? Can I choose adapted coordinates for all of them simultaneously? And the answer is based on the Frobenius theorem again, and the answer is that this is only possible. Suppose that if I have two killing vectors, then there are adapted coordinates simultaneously for k and L if their Lie bracket vanishes. Remember, we defined this when we derived the geodesic deviation equation, and this is partial mu L nu minus L mu partial mu k nu. Okay, and this times this to write it as a vector. Okay, remember that the Lie bracket of two vectors was always a vector, and that was because you could replace this by the Levi-Civita covariant derivative. Okay, so this ensures that this expression is always a vector. Okay, this is important because if this was not a vector, then it would be this would be a coordinate dependent statement, and it may be true in some coordinates but not in other coordinates. So this is really a coordinate independent statement. This is the necessary and sufficient condition for having two coordinates adapted simultaneously to the killing vectors k and L. If they don't sometimes would you say commute when they have vanishing leaf bracket, then you have to choose adapted coordinates for one or for the other. But before I go on, I think I should have mentioned some examples of Killing vectors, because they are not such a strange thing, apart from those associated to these simple shifts. Because Killing vectors are associated to isometries of a metric, every time you have an invariance of the metric, you have a Killing vector. You know the invariances of the Minkowski metric. The whole group, the whole Poincaré group, is the group of invariances, and it is generated by 10 infinitesimal transformations, 4 of which are translations of the form in Cartesian coordinates. Okay, 4 of them are infinitesimal transformations like this. If where this is constant, let me just to emphasize the fact that this is infinitesimal. Let me write epsilon mu. Now I can write this. Remember that at some point we wrote these transformations as the product of the infinitesimal parameters and some parameter independent object or transformation. Okay, we wrote something like this with index mu. Well, this was contracted, so this has to be mu, and then mu, and we said, okay, this is the parameter independent part of the transformation. Now, comparing with the expression, the general expression that I have written before, you realize that this is nothing but a set of 4 possible Killing vectors. Each of them represents is constant. Okay, for mu equal 1, the other way around. For when epsilon is just epsilon 0, clearly this is delta mu 0. 0 only has component 0, and this corresponds to a Killing vector, which is just partial x0 or partial 0. So in fact, you can regard x0 as the adapted coordinate to this shift. The same happens for the other 3 coordinates, so this is not so strange. And now these are the Killing vectors, and there are 4 of them, and the point is that we need to label them, and instead of using, I don't know, a capital I or capital A, the natural thing is to label them with an index nu, which corresponds or coincides with a space-time index. But these are the 4 Killing vectors, and if you want to write them like this, you see that all of them are just this. So the 4 Cartesian coordinates are 4 coordinates which are adapted to these isometries. But we know more because the Lorentz transformations also leave invariant the Minkowski metric, and in that case the infinitesimal parameter was sigma, and the transformations were of this form. And okay, we also said that we can write this in as a product of the parameters time a parameter independent part. Okay. Maybe well, it doesn't really matter if I write epsilon or sigma. I'm sure that you understand. These are infinitesimal parameters, and the way we did it was to consider alpha beta, this parameter, and then this would be eta alpha mu, and this would be eta beta mu. Clearly this is anti-symmetrized, and this has this x nu then. Okay, these are the parameters. Well, we also added this normalization for the reasons that we explained at the moment, and these are now the parameter independent part of the transformations. And now you can see that basically these are just a set of Killing vectors with indices alpha and with labeled by alpha and beta anti-symmetrized, and each of them is given by 2 eta alpha mu beta beta nu x nu partial mu. Okay, now you can, if you lower the indices of x using eta and so on, maybe it gets a bit simplified, but it doesn't really matter. These are a bit more complicated Killing vectors of the Minkowski metric, and these are the ones that generate Lorentz transformations. So we know at least this. We also know one thing, and this thing is that no matter how complicated is each of these Killing vectors that we have here, there exists a change of coordinates such that, well, pick one of them. I don't know, for instance, 0, 1, which corresponds to some boost in the direction 1, a Lorentz boost. There is a change of coordinates such that the same vector now has components just, I don't know, let's call this new coordinate psi only. Okay, and psi will be the adapted coordinate to this particular isometry. Whether this is useful or not depends on the problem that you are dealing with. Certainly for rotations, typically, okay, you consider this vector, and the angle phi, which is the angle that around the z-axis, so the third axis. These are rotations in the plane 1, 2. So this is very useful to represent these rotations or the generator of these rotations through this angle phi. This may not be so useful, but it is certainly correct and possible. Okay, this is something that you do every time you use spherical coordinates. In spherical coordinates, the coordinate phi is the coordinate adapted to the isometry that corresponds to rotations around the z-axis. Okay, now that we have some examples, let's move to the next thing. Now we have a better understanding of what are the conserved quantities or the constants of motion, and the symmetries, and we know that these symmetries, which are in this particular of the Lagrangian, correspond to isometries of the metric, because this is a Lagrangian that contains a metric. And the next question is, what are the conserved quantities associated to each of these Killing vectors or isometries or symmetries of the action? You can apply directly the first-Noether theorem as we described it at the moment, but this just to refresh your mind, varying directly the metric. Okay, assuming that this transformation is of this form, and assuming that k mu is Killing for the metric g mu nu. Okay, so this means that this is 0, and now when we vary the action, we are going to do it in a slightly different way. In this usual way in which we vary the action when we want to obtain the equations of motion. So this first part is exactly what we did before. Plus g mu nu, and then the derivative. Now it was like this. Okay, sorry. We have delta x dot mu x dot nu and a factor of 2. This is what we had. These transformations, for these transformations, delta and the derivative commute. Okay, it is for these transformations. And what we did before to prove that indeed this was 0, when the Killing equation is satisfied, we replace this by epsilon k mu. Now we are not going to do that. Okay, we are just manipulating the same object in different ways to prove different results. We are all the time identities, and if you want tautologies, but this is how you proceed to find results that are interesting. Okay, so now you integrate this by parts, and you also vary this using the chain rule. So This is just okay, I am only interested in the integration by parts because I know that the rest will give me the equations of motion, so I'm not even going to bother to compute them. All I know is that, okay, I have this term. Let me do it. Okay, I have a term that which is the total derivative, and this factor of 2 cancels the factor of 2, and I have d mu nu delta epsilon x mu divided by this square root, and x dot nu, this is the total derivative, and then I have a term which will be minus the psi, and then d mu nu x dot nu divided by this square root. Okay, I don't need to go into all the details because I know, sorry, and this delta epsilon x mu. Okay, I don't need to go into all the details, as I was saying, because I know that these two terms will combine into the equation of motion. We have done this 100 times. Okay, the only term that does not combine into the equations of motion is the total derivative. So this is just this and the total derivative. Okay, and as we said, this is 0, which means, because this is 0 for all the values of epsilon and so on, that you get the following identity, the psi of d mu nu delta epsilon x mu x dot nu divided by this square root is equal to minus ds dx mu delta epsilon x mu. And now let's use the explicit form of delta epsilon x mu, which was epsilon k mu, and here minus epsilon k mu, and you see that this is true for any epsilon, so I can remove epsilon and I get this identity. Okay, here the assumption is that k mu is killing, and this is always true. Now what happens is that if the equations of motion are satisfied, so this is on shell, what happens is that this is a conserved quantity, and this conserved quantity, which we can write as a sort of momentum associated to this killing vector k, is given by g mu nu k mu x dot nu, and divided by this square root that you know that disappears when we use the proper time. And this is the conserved quantity. Now these conserved quantities, in the case of the Minkowski space-time, should coincide with the ones that we have computed before. The standard form momentum and the angular momentum. But it is a trivial exercise to use these expressions that we have obtained here for the killing vectors. This one, this one, and this one. You plug it here and you operate. The only thing that you need to do is to use the fact that now in Minkowski spacetime you have eta mu nu. We are working in Cartesian coordinates. It's just simpler. There's also set, if you want, this square root to 1, so it's proper time. And then you can replace the killing vectors. Okay, so you can say that for the Killing vectors associated to translations. Let's choose a different index. Alpha, you have eta mu nu, and you have k mu alpha, which was a delta x dot nu. Okay, let's see what this is. This is just eta alpha nu x dot nu. Probably you prefer to express this with the index alpha up, so this is just the standard momentum up to the I didn't add the mass factor, but this is the standard momentum, and you can do exactly the same, but with some more indices and antisymmetrization for the Killing vectors associated to infinitesimal Lorentz transformations. A final observation on this topic. You see that life in Minkowski is happy and funny. You have 10 conserved quantities to play with, and so you can characterize the motion of your particles in different ways. And most importantly, you have concepts like energy, which would be the conserved quantity associated to translations in time, and these kind of concepts that really we appreciate as physicists. But what happens if your metric does not have an invariance of such as time invariance under time shifts? Well, more generally, you could say that okay, this is because I don't have I'm not working in adapted coordinates, okay, and I have dependence on time, but this may be artificial. The question is that you could find all the Killing vectors of your metric, and it may happen that you don't find a Killing vector which is time-like. So you need a Killing vector which is time-like, in our case like this, in order to say or to construct an adapted coordinate which you can identify with time. Okay, if the vector is not time-like, the adapted coordinate will have another interpretation. When the Killing vector is like this, then the metric will be independent of time and so on. But if there is no such a vector, there is no time-like Killing vector, there will not be a time coordinate such that the metric is independent of it, and there will be no conservation of energy in that for the motion of a free-falling particle in that space-time. This may sound strange, but you see, when you consider a very general metric in which this can happen, you are also considering a very complicated or a very general gravitational interaction between the gravitational field and the particle, and the transfer of energy between one and the other, which is not taken into account by this, because you see that the particle reacts to the gravitational field, but the gravitational field does not know anything about the particle, could be important, and then this energy would the energy of the particle alone could not be conserved. In general relativity, the issue then you would have to consider also the conservation of the energy, the total energy, the energy of the gravitational field. But in general relativity, we said that there were a lot of problems to define the energy of the gravitational field. This is a very complicated issue, and the only solutions that we have are you either consider the total energy of the space-time, okay, or you study approximations and you deal with the energy in a special relativistic limit. Well, the situation is complicated and probably is not completely satisfactory, but this is what we have right now.